So, hello everyone. I am Emanuel Podetsianakis. I work for the media coding and delivery team for Xiaomi, part of the new technologies and standards. And I'm going to present you the work that we are doing with my colleague Emmanuel Thomas on video extensions for XR applications. So this is the outline of my presentation. Basically, we're going to start by showing you some examples about different XR applications and their requirements. Then we're going to talk about where the Vulkan video extension fits. And then since we are doing also standardization about MPEG, we're going to show you a work we are doing on video decoding interfaces called VDI, which is MPEG-I part 13, the working name, where those two technologies, Vulkan and VDI, fit together. And we run some tests to show performance that we have for XR applications before we're moving on to the future work and the conclusions. Beginning with some application examples and what kind of requirements they have. First off, by saying XR, we mean VR, MR, and AR, virtual, mixed, and augmented reality. In this context, we mostly focus on AR, and specifically on standalone AR glasses and different applications for that. But going back to the example applications, we can have something that most of you know, which is like a VR virtual environment. And it uses different assets like 3D models and video overlays that have requirements like high throughput, synchronization between assets, both spatial and temporal, and they require multiple decoders if you're having different videos. For AR conferences, which is a very simple AR example, typically you have something like which is color and depth streams that you might want to do for different functions like post correction. And again, we have the requirement of multiple decoders because typically depth is also decoded as video. So you usually have one color video stream and one depth stream. And because we are talking about live conferencing, you have low latency requirements. If we go to XR gaming, we have pretty much all of the before combined, which is a very, very demanding application. Moving specifically to the example that we're going to take as a given for the sake of this presentation. As already mentioned, we have multiple decoders. Even in very, very simple use cases where you only want to see a user with the depth, you will have at least 2 decoders. And there are several uncertainties about such systems. So the number of decoding instances that are available at runtime, you might have different resolution per stream, you might have different codecs, and you also have to synchronize this output. So when we are talking about something like this on a very light device like AR glasses, similar to those shown in the screen, it's not very easy to do at all. Over here we have an example what happens when you have like 2 streams that they are not perfectly aligned. So over here we have rendering of the depth stream and a video stream. And as you can see, the hand, the color representation of the hand is not at the same spot where the depth representation of the hand is. And this is regardless of what happens on the application level. Basically, this is just rendering of one device capture. So imagine what happens if you have like different sources of different devices. This is a very, very rough overview of the Vulkan video extensions. I'm not going to stay long on this since our colleagues already made a significant mention. Basically, we mostly care about the video decoding part since this is what will happen on the AR devices. And we want to, the good thing about Vulkan Video is that the way it manages the decoders is very, very convenient if you want to have like a full-blown AR application. Basically, you have besides the codec parameters that you input, you also have management of the buffers, etc. Functionalities that could be very useful for an application developer. And this is the work we are doing in MPEG within the video decoding interface group. So basically what we are trying to do is we're trying to create an interface for the application that it doesn't have to manage multiple decoders. As mentioned already, like at least 2 decoders is something that will be common in the future. So we're trying to define a way that you will have management of these decoders by an interface to the application that is going to be very straightforward and would not require much from the developer to give consideration. This is the very, very high-level architecture diagram we are using in MPEG to describe VDI. And basically, whatever you see on the boundaries of this box, meaning the input video decoding interface, output video decoding interface, and video decoding engine, is the interfaces to the application. Everything inside the box is what should be managed by VDI itself. The different streams that you see is not so much important in the sense that, for example, the metadata stream is basically for now a pass-through, since we want the application to have access for it, while the elementary stream creation, for example, should be handled not by Vulkan. These are some of the goals that we have in VDI. So we want to group the decoder instances together by the interface we saw in the previous slide. We want to be able to do some merge and split of the bit streams. When we are talking about bit streams, we mean purely the encoded video bit stream, and output decoded sequences in synchronized fashion, meaning that multiple decoders might have different streams and different speeds. So you might want to not care about this. So VDI will take care of it. And the last bullet, which is important, is that VDI builds on existing technologies. So basically, we're not defining a technology. We're defining a way of using this technology. And Khronos Vulkan, and specifically the video extension, is one of the technologies that it has a professional mapping in the spec. Other examples, for example, could be the media source extensions for the browsers. This is a very, very high-level architecture of where VDI and Vulkan fit together. So on the top, you have the XR application. Where you have the black arrows is the control commands for the VDI. And you can see that on the blocks close to the bottom, basically you have hardware decoders, VDI and Vulkan video extension sitting together, meaning that this is what creates basically the actual decoding capabilities. And after that, you have data exchange with the application about the encoded and decoded streams. So what we're going to show you today is some tests we did on decoding for mobile devices. So we are Xiaomi, and we are doing like mobile devices in general, but we specifically now test in smartphones because they have some similar capabilities with what we expect to be in AR glasses. Notably, limited processing capabilities, energy consumption is essential. You cannot go to full processing for a long duration of time. They share the same family of chipsets, etc. So by evaluating performance in smartphones, we're hoping to get insights about performance in future AR devices. The motivation was to see the benefits of Vulkan VDI extensions and how it could be potentially combined with VDI for XR applications. The target, again, was to measure performance and scalability of such devices. The methodology we did was to measure the decoding times of individual frames using the Android video decoder. This is the current alternative to the Vulkan video extensions because Android doesn't support Vulkan video yet. So basically, what we're going to show you now is the state now in Android, hoping to come next year with the state of Vulkan video in Android. The tool we use for that is the VidBench. We call it VidBench. It's an in-house video decoding benchmark tool we built in Xiaomi for Android, basically for the purpose of these experiments. The device we selected is, again, mobile devices for the capabilities, and they are they are two different devices, as you're going to see later. The content itself, it's AVC, also known as H.264 encoded video. To be more specific, it's the Big Bad Bunny, the same video that you saw in the previous demo. The duration of the video was 2 minutes, and we did 2 encoded versions. One is iframe only. Iframes are standalone frames, meaning that in order to decode them, you just need that frame, no dependencies before or after. And another one, which was iframes and pframes. So pframes is might have dependencies of frames that came before that. The first one is very similar to what you would have in a very live-like scenario, but it's not commonly used because the encoding performance is not very good. While the second one is what you would have in typical low latency scenarios. This is why we selected to do those two. A little bit about the VidBench tools, since it's not public yet, so you have not seen it. Basically, it's using the media codec and media format APIs of Android. It takes it's a single thread per decoder, which is the reason we wanted to try for the multiple decoders. The user defines the number of decoders per test that wants to run. The user defines the number of runs per test that wants to be run. And basically, we're going to show you the specific settings later. And we observed that we can have up to 12 input buffer slots, and each test we did was for 20 runs. As you can see, there is a benchmark thread running. Inside that, we have the run threads which handle the decoders. The bit stream is parsed from VidBench, so we're not worried about that. And then you have different buffers from the media codec for the decoders. This is a pseudocode with some about the video launching. So first, we're getting the input buffers. Afterwards, we're writing the null unit to the input buffer. Null unit is the smallest unit you can have of a frame, basically, before you go into the decoding step. We queue the null unit into the input buffer. And when the decoding is done, we're getting an output buffer, and we release it immediately since we are not doing any post-decoding processing, which would be one of the advantages of Vulkan Video, the fact that the post-decoding processing should be very straightforward. This is what we observed. So in what you are seeing now in the center is a bit of a graph about how it performs in the I-frame only scenario, using 1, 2, 3, 4, and 5 decoders with a mean decoding time. And on the peripheral graphs, you can see the actual form that the decoding takes. As you can see, even with 2 and beyond decoders, like the performance degrades significantly. And also importantly, the standard deviation of the measurements also increases, which means that it creates an unpredictable behavior. So when you're building an application, you don't want to not know basically when your frame is going to be decoded. Moving forward, this is what we did, the test that what we observed between the 2 different encoding parameters. So on the left, you would see that it's the one that doesn't have dependencies, basically the same as we saw before. And on the right, you would see the one that uses both P frames and I frames. Even though the one on the right is what is more commonly used, we can see that the performance is even worse, which is basically bad news. And we can take the conclusion that basically the encoding parameters are very, very important on how an application will work, which again, it's not good news. The final experiment we conducted is we tried with 2 different devices to see how this would affect. What you saw before was from the device on the top. Basically, it's 1 generation before the other device. But those 2 devices do not have bad specification, meaning that they should be able to handle these tasks easily. And this is what we get for both video streams for both devices. So the green lines are basically the newest device, while the blue ones are like the 1 generation before that. As you can see, there is some improvement in performance. However, I don't think that it's significant enough, especially since, as you can see, like as soon as we scale after the 1 decoder, the performance is really, really bad. And on the right, that you can see the graphs. Note that the Y scale is logarithmic. You will see that the devices also have different decoding behavior. So we didn't manage to actually explain how this happened, like why in the first one we have like a more smooth but fatter curve, while in the other one we have like more points. But what we do know is that the fact that you have this uncertainty is not good news again. So where does this leave us? This leaves us in the point where we have to do some more work, obviously. When it comes to benchmarking, we want to have more tests with different codecs. Different codecs, we mean both different video codecs as well as different codec configurations. And we would like to port VidBench on a Vulkan-based platform as soon as it is available, because for Android now, basically, we do not have any options on that. And personally, the first test I would be curious to conduct would be what would happen if we have mixed assets, meaning that Vulkan video extensions should be able to take care of the decoding, and after that you can use video for shading and geometry, and then we can actually be able to make a realistic test about how it would look developing an AR application on mobile devices. Regarding the VDI standard that I mentioned before, basically it's been finalized these days, and we're expected to the first version to be released soon. While we have already started discussions about the second edition of VDI. So the second edition should extend support for other codecs. It will define metadata streams that they are essential, and will have a validation and conformance framework. Having said that, Vulkan video extensions, if they come up for Android, we do have time to take it in consideration in the second edition of VDI. While for the first edition, we basically did some essential mapping. And that's it from me. Do you have any time for... Yes, I think we'll have some time for questions, right? Yes. Yes. HD. 1080, yes. Sorry? The average time was somewhat like 100%. The average decoding time? Yes. For how many decoders? Basically, we can... It's what we saw, maybe we can use this one, is that it's barely enough. Keep in mind that this was in a null unit per null unit basis. So as we heard from the presentation in NVIDIA, this degrades a bit the performance. So this was not optimized and it was not rendered, meaning that the performance of the decoder, it doesn't seem to match what is required for actual video playback, which is not the case. So all these graphs are indicative. It's not an actual benchmarking test. This is why I avoid using the term benchmarking for what we did.
I guess my question that decoding time seems to be quite high.
Yes, exactly. So normally this shouldn't work, but it has to do with the fact that when you just do video playback, you just pump up whatever you have as soon as it arrives, and you expect the decoder to give it the result for rendering. But if you want to have XR applications, this will not be the case, because you might put a frame, wait for it to come out, then do some graphics processing and then rendering. Or you might have different frame rates between the video and the graphics. So I would not take these values as an actual test, but we mostly care about the form that they have, how they scale. Any other questions? All right, thank you very much.